introduce Mr. Sharma sir. So Sharma sir is an AI engineer. He has worked on various projects and products in image and text processing, and he has created and deployed 50 plus microservices on AI models for applications such as face recognition, facial expression, identification, diabetic detection, NLU based chatbots for various industries, and small talk conversion and chatbots for NLG based poem generation. And Sarah has completed his BE in Anand Institute of Air Technology in the year 2014, and he has completed his PG in PSG College of Technology in the year 2016, and he has been working as an assistant professor in the year 2016 to 17 in Vinayagam's universities, and he has been a AI researcher from the year 2015 to 16 in Habino, and now currently he is working as an AI technologist in agents.ai. He mainly involves in design and develop the AI and microservices for the NLU based SaaS products, and maintain the AWS infrastructure for the development of products, and contribute to the development of UI for the applications of AICTE, and create meaningful dashboards for the customers to get insight about the performance of the chatbox. And Sharma sir, can now I hand over the session to Sharma sir. Sharma sir, kindly take over the session. Thank you.
Thank you, Vivek. It was an lengthy and good introduction about me. Yep, thank you so much. So I think I can directly get into content. So if you have any questions, you can just send me your questions on chat so that I can answer in between, right? I think you can see my screen. Yes. Okay. I think you can see my screen, I guess. Yes. Is that
Yes.
Yep. Okay, fine. So on top of that, I know heard about all about me, and yeah, and it's to be very precise, I'm just a technologist, and I'm just handling couple of startups on technology. That's what I do. So my entire thing was in and around artificial intelligence, right? And this particular session for the next 1 hour, so we are going to have a session about autoencoders. It's one of the beautiful topics in artificial intelligence, right? If you know what exactly the autoencoder is and when and where you have to use autoencoders. And it's not an it's not something like algorithm to train or something, but it has a lot of application. But when you consider other algorithms, other setups, they have probably one or two applications. They may have one or two use cases to solve with that particular algorithms. But if you think about these autoencoders, right? So you can do a probably more what do you call number of use cases. You can solve more number of use cases. You can handle more number of applications and all these things. Okay. Right. So what's the point? What exactly this autoencoder? Why do I need to have autoencoders? So the name suggests it's an encoder. That's it. It's an encoder, and you can have a decoder. And ultimate, applications of this particular fellow is to compress and raw data, compress an image, and if you want to remove a noise, you can do that. So it's just a kind of compression scenario. That's it. If you want to compress certain data, you can use autoencoder. And autoencoder is generally an unsupervised machine learning stuff, which is nothing but it's a neural network. Autoencoder is based on the neural network, and it comes under unsupervised machine learning cases. The job is to reduce the size of our inputs. That's it, into very smaller representation. You can assume that I think I have an example. For an example, I'll tell you, if you want to compress and image of HD image to some low quality image, you can do it without losing any kind of informations. You can still have the same information. You don't need to lose any in some scenarios. And the other thing is you can reconstruct the same uh, stuff from the encoded data, when I can say from the compressed data. So that's why you can see it's a 4 here and still it's a 4, and you can see the almost these two images are almost same. And here I'm just encoding, here I'm just decoding. So this is our raw input, this is our reconstructed input. Raw input is encoded, and then from the encoded input we are decoding it to get the reconstructed input. And you can see it's almost equal, x and x dash is equal, which means encoded and the reconstructed is almost equal. Okay, so that's what it is. So we can see our input image, we'll go through series of block to get it reduced size or in a smaller dimension, and then from again we will have a series of block to reconstruct the same image. But one thing, it will degrade the quality of an image, obviously, because whenever you do a in shrinking and expansion scenario, obviously you will lose some data. But it does the same. Your data, the reconstructed data may be an what do you call, maybe an degraded stuff itself, right? So that's autoencoder. But as I said, and you may think, okay, why do I need to use autoencoder here? I may go with an other encoding and decoding technologies, right? But here you can see the name autoencoder, which means you don't need to do anything from the particular stuff. It does it everything on its own. You don't need to do it. It's something completely automatic, and it learns what to remove, what not to remove, and what to keep, what not to keep. So all these things it knows by understanding the data. You don't need to do any manual configuration here. All you need to do is you have to create an architecture for these auto encoders. So the one, then that auto encoder will does the job for on its own, right? Okay, you might have heard, okay, even a PCA does the same, right? Then I can go with PCA, which is very simple and which is very pretty straightforward. Then why should I go with autoencoder? PCA is less complex, whereas autoencoder is more complex than PCA. But still, you may think, oh, still you may think like, I can go with less complex algorithm. I can go with PCA stuff. Why do I need to have a complex algorithm like autoencoder? The answer is very simple. PCA can do any sort of analysis only on the linear data, right? Very, 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 very common difference is PCA can do the same analysis only on linear data, whereas this autoencoder does the same on non-linear data as well, because it has non-linear activation functions. So it does that part also. And the other thing is it does not have a dense layer in the sense, so it doesn't have huge neurons and huge layers to learn and all these things. It has a very minimal count, minimal set of layers, and moreover, it has from the first layer is around 100, the second layer will be around 70, the third layer will be, so it will reduce the size as you go through the encoder. That's the other advantages of using autoencoder. And then you can use convolution autoencoder. If you, let's say you are dealing with image or video, you can go with convolution based stuff. If we are dealing with some other text, you can go with other neural network stuff. You can change the internal algorithm, so internal operations, right? So I'm sorry, so you can change the internal operation, so all these things when you use autoencoder. And obviously PCA is a single layer stuff, so you don't get that much efficiency when you compare with autoencoder, because autoencoder is, as I said, we have a series of blocks, series of layer to process. To each layer learns better than previous layer, so at the end we would have a more efficient stuff, right? And PCA does take one input, and it does give one output. Maybe at the any starting of the process, it takes input. At the end of the process, it gives you an output. Whereas autoencoder, you can take output from each layer. Let's say if you want to have an output at the end of the encoder, you can have it. At the end of the code block, you can have it. At the end of the decoder, you can have. Even in between layers, if you want, you can have it. And I mean, it's what do you call? You can use pre-trained layer, which means you don't need to train from the scratch. You can just grab some pre-trained model. You can take some pre-trained layer, and you can infuse with your encoder or decoder just to increase the scenarios, right? So now we know what is autoencoder and why are we using autoencoder rather than PCA. Now you know all these things, right? Okay. What are the application of autoencoders? Why should I use autoencoders, right? So do I have any dedicated use case? Yes, you have. Image coloring. So image coloring, so it's not an is easy way to convert a 3 channel into single channel image. Means from color image to grayscale, it's very straightforward, very simple, because you have one line of coding, you can do it. But the reverse is not that much easy. So what you have to do is you have to write an algorithm to convert a black and white image into color image, but that can be done using autoencoder. So autoencoder understand what each understand the object in each in this image, and then it understand what color it should give to each objects, right? That's the first application, image coloring. Feature variations means you can see the input image has the noise, and the decoded image, the output doesn't have any noise. You can see that light, right? So that's what feature variation. So you can skip, or you can add more features, or you can skip the feature that you don't want to proceed, right? So what they are doing is they are just ignoring that particular portion of data, and they are interpolating with the nearby data so that they can reconstruct the image. That's a other scenario. So this is what feature variations. And then dimensionality reduction, that's what I said. You can see here this has 100 kb, the 1000 cross 1500 cases as a 100 kb. Okay, and if you do a auto encoding scenarios, you can have is a on the same dimension, but it is 25 kb. You can see that does not reduce the quality or something like that. It has restored everything, but lesser dimension for each pixel. It reduces the dimension of the pixel, right? That's other advantage. That's I think third application. The fourth application is denoising image. Denoising image is, you have to understand, it's easy actually. There are different Gaussian noise, salt and pepper noise. There are a couple of noises we have. You have to understand what noise it is. You have to remove that noise based on the noising term. That's what we do, in a conventional way. But if you use auto encoder, you can do that automatically, because if you give a noisy image at the end of the decoder, you will have an image without any noise. You can see that. So it is reconstructing the image based on the features. And then watermark removal, and watermark removal also is possible. You can add and remove. Again, adding a watermark is very simple on image, but removing it is very difficult, because you would remove the what you call data, or maybe a useful pixels. There is a chance to remove them. So that you have to be very cautious when you remove a watermark. So autoencoder does that. So these are the highly used uh, applications for autoencoder. And you can think, yeah, okay, all these are for image. Text is very simple. Handling a text or vectors is very simple, but image is not. So these are the applications on the image processing side. Now we know what is autoencoder, why we are using autoencoder, and what are the applications of autoencoders. Now we have to understand the architecture. If you understand the architecture, you can add or delete. You can modify the existing architecture, and you can use it the same autoencoder for different applications, but only if you know the architecture. Okay, that's what we are going to see, right? Architecture, design, pattern, whatever you call, but in industry we call just as a architecture. So architecture is very simple. There is only three component. One is encoder, the other one is code, other one is decoder, right? Encoder, do I have an image? Okay, sorry. So these are the three components. The first off is the encoder, center part is the code or coder, and the last portion is called decoder. The encode, we know it will encode the image, it will compress the image, right? That's what we know. That compression, in technically we call that as a latent space representation. It's called latent space representation. So we don't latent in the sense internal or internal stuff. It's called latent. So what we do, what this encoder does, it converts. It's not actually converts. Converting. It's compressing. The process called compressing. The encoder compresses the input images into latent space representation or latent space vector, right? So compressed image is not as good as the input image, because it's compressed, and it is called disordered version. Disordered version is um, we don't have an order. It's like jumbling scenarios. The other side, in between we have a code. So code is the gate. It's just a gate which will think and allow the values to the decoder. So code does not allow all the values from the encoders to decoder. Instead, it does allow based on certain validations and all these things, right? And the other part, decoder, is the exact opposite of the encoder. From the compressed image or from the compressed data, it has to reconstruct the original data. But as I always, or as I already said, we will have a degraded version of the input image. So degraded version of the input image. That's what we'll have. And the code is the one. The code is very important. The code is what we call as a hidden layer. We can consider this way. If you know input layer, neural network, we will have three different layers: input layer, hidden layer, and output layer. In this autoencoder, you can consider the encoder as input layer, decoder as output layer, and the code is the hidden layer. So code, the number of neurons in the code block should be very, very, very minimum as possible, so that it will reduce them. It will have a good compressibility or compactness of the model. That's what you can see. The definitions, all these things. So original image and its reconstructor from latent space, all these things, right? Or you can see that bottleneck. So input layer, hidden layer, and output layer. Input layer is nothing but encoder, and output layer is nothing but decoder, and your bottleneck is nothing but code called hidden layer, right? Like properties. What are the properties of autoencoder? Okay, data specific. The first thing is data specific. It can compress, decodes, encodes, whatever the term may be. It does a particular job only on the data it has been trained on. Okay, they don't for other neural network, you can train the data model on some other data set, and you can try with different variations of the same data in your test phase. It works where they work, but these auto encoders, they don't. They will work on the data only only on what they have trained, what they have been trained on. That's a data specific. Lossy, that's what I'm telling from the beginning. Like, we would have a lossy data. We will have a degraded data when compared to the original input, because we are reconstructing the image from the compressed version, right? And then it's automatically, that's autoencoder. The term is called, like, automatically it learns from the set of data or with a specific type of input, it learns on its own. We don't need to do any manual operations. These are the properties of the scenarios. Okay, hyperparameters. I don't know if you know what is hyperparameter. Hyperparameter tuning. That's actually a nightmare for an ML guy. So it's not easy to find the hyperparameter. So you have to tune all your parameters, and then you have to understand the trade-off between all these things. So once you know how to tune the hyperparameters, I know in a way like tuning a parameters in such a way that tune value will give a better result, then it's called hyperparameters. That's it. Okay, so tuning a parameter is not an easy job. No, even creating a model is easy, but hyperparameter tuning is very, 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 very simple. That's why I named that as a hyperparameter hunter. You have to hunt it, you have to wait, you have to find, you have to trial and error, you have to go on trial and error basis, right? So that's what hyperparameter hunter. And here we have 4 different parameters. Okay, so, this how it that's what I said. It's not easy job to find the hyperparameters, right? These are the common memes. When you can see the frustration in the first meme. It's not easy to find the hyperparameters, or it's not easy to tune and parameters. The second thing, one does not simply pick hyperparameter. You cannot randomly pick an hyperparameter, because if you do that, you will face see the trade-off. And this is I think my favorite types of headache, right? So when you have migraine, you have only one portion of head will give, you feel the pain. The hypertensions, again, the backside. Stress maybe in one direction. But when you tune the parameters, when you tune the hyperparameters, you feel the pain, and you feel pain in all over head. So it's very uncomfortable situation. If you are in the ML field, you would understand how uh, worst it is. Okay, coming to this content, as I said, we have 4 different parameters to tune. Do I have a definition? No, I don't have definitions. Okay, we have 4 different parameters to tune to have a better autoencoding performance. One is code size. Code size, as I mentioned, the center part of an autoencoder is called code. So if you have as minimum as number of neurons in the code, you will have that much good compression. For an example, if you want to 1:100 compression, you need some X number of code size. If you want to have 1:1000 in one compression, then you need to have X square or X cube number of it's like as minimum number as small as the code's value, you'd get that good compression scenario. Number of layers, and the number of layers is nothing but the number of layers in the encoders, number of layers in the decoder. You can have any number of layers in the encoder, you can have any number of layers in the decoder, but more you add the layer, more the complex your encoder will become. So more complex, more computational power it takes, and more time it takes to train the particular data. And number of nodes per layer. For example, if you want to add 100 layer in the encoder, and the second 200 layer in the next encoder layer, is good. You can add anything, but as I said, the nodes should decrease. It should reduce. You should have a reduced number of decretion when you travel from encoder to code. Again, you should have more increased version of layers when you move from code to decoder. Okay, and then loss function. Loss function is nothing but just to evaluate your model. So it's like either like you can use mean square error, root mean square error, or you can find the accuracy, whatever it is, based on your applications. So 4 different parameters here. You have to have a concentrations on that. So you can have any number of layers, you can have any number of nodes, can use any loss functions. Again, you can use any code size, but it should follow certain regulations. That's it. Okay. Next is types of content. What is the types of content? It's nothing. Types of autoencoders, right? So what are the different types of autoencoders we have? First thing, it's called convolutional autoencoders. Convolutional autoencoder, you might have understand, it uses convolutional algorithm, right, to do this particular operations. Okay, so convolution operation is you know there is a say some like people say you cannot learn anything from single signal, or you cannot get any data from the single signal, right? That's what people say. But convolution does the same in the opposite direction, which means it learns each and every feature from one single one in a very limited number of signals, right? So convolution operation is that. So it learns from the limited number of signals. So the entire block has a convolutional layer in between the code and encoder layers, as well as in the decoder layer. A use case of convolutional encoder, you can use this to reconstruct image colorization, which is nothing but converting grayscale into color. And then latent space clustering. You know what is latent space? We know what is latent space, right? Because encoders, whatever the encoder you have, it does convert your image into latent space representation, which is nothing but the vector of a same image in a different order. If you want to have a if you want to have a group in that class data, then you can use latent space clustering. It's one of the applications of use case of convolution and if you want to convert a low resolution image to high resolution image, you can use this autoencoder. The next one is sparse encoders or sparse autoencoder is almost same. The only difference is you can have more number of code size. The central layer is called code. Okay, it has more layer, more number of neurons. So this reduce the bottleneck. So you don't have any bottleneck here. Okay, so we don't have any special use case about this sparse autoencoders, because anyway they have they use more zeros, right? So to reduce the complexity, because they are adding more neurons, so obviously it would increase more what you call complexity. So to have that, you can reduce that. Okay, and then autoencoders, deep autoencoders. And deep autoencoder is nothing but having a neural network which have more layers of neurons and neural network, right? And in fact, this is the first autoencoder. This is the first autoencoder. It's generally based on MLP, multi-layer perceptron. Okay, so multi-layer perceptron. So you can have first 3 layers as encoder, last 3 layers as decoder, and central layer is called code. This is a first and simple encoder with the neural network, and you can use this on image search, data compression, and topic modeling. If you want to get one particular topic out of a data or out of a text, you go with this particular stuff. It's called topic modeling. So deep autoencoder is the first thing, and then they come up with the convolutional autoencoder, and then they are using a sparse encoder. But I don't feel like using a sparse encoder is good for your use case, because it increases your how do you call it? It increases your complexity. There are other couple of autoencoders are there, because that's are where less often used. It's rarely used case scenarios. Now it's a time to code. So we are now going to codes. Okay. So code what? Code autoencoder using Python and then using TensorFlow. Right. That's what we are going to do now. So I'm going to use Colab because Colab is an online tool. Where you don't need to install anything. So I'll take. I just going into collab.research. It will get you this page. I'll search for autoencoders. Yeah. Oh, these many autoencoders. Oh, I will open a new notebook here. I have a code. So you can just click this connect, and this is basically running on Intel. So what I'm going to do is I'm going to change the run type to GPU. So I need GPU for this, so I'm going to use GPU. Since you are getting connected here with GPU, it's connected. Python is running on Python 3 is running on GPU. So I have a more RAM and then I have a more space. I This is a code I'm going to use. I'm going to use an TensorFlow. In that, I'm going to use Keras, and from TensorFlow, I'm importing in the layers. So TensorFlow has all the modules, whatever you want, you can use this. And what I'm going to do is I'm going to use inbuilt data set, that is MNIST digit recognition data set. This is the data set I'm going to use for this demo. It's an inbuilt data set. You don't need to load image. They have this image inside TensorFlow, so I'm going to use that. So for that, I'm going to define my encoder, and then what is this? I'm going to encoding dimension is 32. No, so it's simple, 128, 64, and encoding dimension. Again from 64, 128, 784. This is what our in between layer. So this is what our code. So this is what our encoder and decoder. Right? So you can add any number of layers. I'm just adding a simple case. I'm not going for multi-layer. I mean, I'm not going to use convolution autoencoder. It's a simple, deep autoencoders, right? So you can here I'm using keras.model as autoencoder, decoder as the entire stuff as the model. So you can see I'm giving decoder stuff as the encoder, I mean auto encoder. This is our final scenario, and this separate stuff. Two different model you can see. One is auto encoder, other one is encoder, and this is our input. So you can see that same input here. Okay, this is for defining two cases. I'll show the summary. This is encoder summary. So we have 1784 input layer, that is to 128 layer, then 64 next 32. And if you want to have decoder summary, this is what decoder summary. So we have 128, 64, 32, 64. This is our entire model. So starting from the input layer to the output layer. So you can see this is 784, 784, 128, 128, 64, 64. This is the code. So code is 32 here. Right? This is our entire autoencoder. This has both encoder and decoder. Right? Right. I'm taking different separately for decoding here. So decoding is nothing but our all the layers. The autoencoder, you can see this. So actually it is from 64 to 128, 788. These are our decoders. Let it be. Okay, now we are going to combine with this stuff. I'm using optimizer. Optimizer is nothing but to update the weights. So to update the weights, you need a. Oh, I forgot. Do you have any notes? Okay. To update the weights, we need to have Adam, and this is our loss function. Binary cross entropy is our loss function. Now we have created our model, which is autoencoder. So autoencoder is nothing, is our model, right? This is our model. It's our model. Now what we are going to do is we are going to get the data set. We are going to get the data set. As I said, we are going to load the inbuilt data set. This is what I'm taking inbuilt. I'm just taking only train and test image. I'm not going to take the label. Downloading. Yes, it's done. I'll show one image. So this is the first image, 5. Okay, this is the first image, 5. Right, this is the first image. You can see that. You can see 5 is the first image. If you change the number, I'll take the 5 number, the other image 2. Okay, we are going to encode this, and then we are going to decode this. So encode, then we will do a decode. So for that, we are going to do a processing. Since we are going to use GPU, I'm converting a data into float 32, and then normalizing the data by 255. So it's just a normalization, and you can see the shape is 60,000 images in training, and then 10,000 images in the testing. Now what we are going to do is we are going to convert this into our model. So we can see extrain 10 epochs, 256 is the batch size, 10 epochs means 10 iterations, and every time it should shuffle the data, and then our test data. Model will get trained. This is the first epoch, second, you can see the loss. The loss is around 0.1. Okay, the loss is around 0.1. Now what I'm going to do is I'll show the encoded image and decoded image. Encoded image and decoded image. I'm giving the test data to encoder to get the encoded image, and same for the encoded image I'm sending to decoder to predict the decoded image. Encoded image, decoder. Sorry. So sorry here. To is I'll get this response. So meanwhile, I'll first show the input and encoded image. So then I can show you the decoded image. Mm-mm. Finish that. So all getting spoiled because of this decoder. I'll skip this for now and change the model to convolutional decoder so that I think it will work now. This is what noisy data. So what I did is I created a noisy data for extrain. So the original data I'll show you. Um, this is the original data. This is a noisy data. So what we are going to do is we'll remove this noise, right, using a convolutional autoencoder. So for that, instead of dense layer, what I'm going to take is convolutional 2D. So convolutional 2D. So here you can see the model has dense, normal deep encoder. So here instead of dense, so we are taking a convolution scenario. So 1, 2 convolution in the encoder side, 1, 2 convolution layer in the decoder side. So we are taking encoder and decoder and combining to a one particular model. So I'll show this, I guess. This is an autoencoder for using convolution autoencoder. You can see 28, 28, 14, 7. See again 14, 28. This is how it is going front and back. Now we train this data. So here I'm giving noisy data as well as original data, noisy data as well as original data. So only 7 epochs. Let's train. So meanwhile, if you have any doubts, you can ask me. So loss is almost, we are getting same loss was 0.1. It's done. I will see noisy and then denoised. Same image, noisy and then denoised. Okay. So this is what we are input. This is what the reconstructed, right? So original is this. It gets noisy. We added this noisy input, and then we train with noise and denoise stuff, and we are getting this particular. This is not noise removal, so you don't see any noise here because we are getting them denoised. So denoised is nothing but our model is predicting our noisy input. That's it. We are just giving a noisy input to predict, right? So now I'll try to check it out. This model 784. Encoding dimension activation ReLU input image, and then decoder into, and remove these two. I come on this one. Autoencoder model input image decoder, and encoder equal to input image. Okay. Now check out. Encoded summary. I have only one layer. Encoded input is done. Autoencoder is 784, 32, 784. So these are our layers, right? And then autoencoded layer -1. Input. Input is our decoder. Encoded input is dimension. I got it. I got it. I got it. I got it. So we have now a decoder is 32784 compiled. We'll do the analysis now. Okay, so encoded image is this, and this is the TX test, and then decoded images same 784. So what we are going to do is we are going to plot the encoded and decoded cases, original and decoded. If possible, we'll plot the original image. I try to plot original and encoded image. This is original and then encoded image. Oh, no. So original and decoded image. I'll show you the encoded image. Encoded images. Oh, it's 32. Right. Cannot do this. Okay, this is what the decoded image, right? So this what is a decoded image? So original image, and then we encoded into the. So this image is 28 cross 28, and then we decoded into encoded into 32. Encoded into 32, and then from 32 pixels we are reconstructing to 784 pixels. So the entire stuff is 784, 32, 784. So here what I did is I removed few layers. So it's our input image cases. So you can add more layers, but if you add more layers, you have to be very careful when you design the decoder. So we had issues in the decoders because we didn't have a equal number of layers in the decoders. So that's the issue we had. So if you want, you can add these two. You can just command these two, and then you can add all these things, right? So you can just add this encoding dimension here. That's it. So you can try different this, just to command this, and then you can uncommand this, and you can check it out these scenarios. So ultimately what we are trying to do is two options, two things we have done. From the original image 784 to we converted into 32. Okay, and then from 32 we have converted back to 784. This is the first step, first use case we did, and the first model, this is what it does. It did. The second model is we have noise image, right, and to be no noise image. That's it. This is what we did. Okay, using encoder and decoder, we have a noisy image. At the end, we removed the noisy. That's what you can see. So in all these things, we have an intermediate surface 32. I mean, here you can see that 32 is a dimension, but 7 cross 7 is a image type. Okay, so 28 cross 28 to 7 cross 7 again backs to 28 cross 28. Okay, so and this is what is happening here. So two example, one is for noise removal, other one is for encoding and decoding. I'll add this here. So this one is okay. So this one is simple deep encoder, and the other one is cases. Right. I'll share this notebook, and then I'll also share this PPT so that you can try. So for the first model, again, you can try with by removing commenting this and then uncommenting these things, right? So you can try different things. So these are two different cases, and you can try for other applications, as I mentioned, like image. So you can try with the image coloring, decoloring, and then you can even have a dimensional reduction, all these things. Okay. So that's the thing I guess I have for encoding, right? So you can connect me at, you can connect me on LinkedIn, and you can check it out my company website, and then you can check it out my personal website, just sarmasaravanan.com. So you can just connect me on LinkedIn if you have any doubts, or if you have um, any suggestion for your research. You can connect me on LinkedIn. So that's it. I have it. So check it out my website, and then my it's sharmasaravanan.com, and then you can check it out my LinkedIn, where I keep posting about all these ML and other things. Even sometimes I do share about opportunities. So that's the thing. Okay, I think I have that thing. Thank you so much. And if you have any doubts, you can ask me so that I can help you with your doubts. Thank you, Renuka. Thank you so much for the feedback. Then, so you can share me your feedbacks if you have, or you can just ask me any questions.
Participant, if you any doubt, kindly ask to him, or otherwise put to the chat box. Okay. Okay. Thank you, sir. Thank you very much for accepting my invitation. Right. Nice presentation. Thank you,
Thank,
sir. Thank you very much.
thank you.
Thanks.
So I will share all these materials so that you can share with them. Right.
Okay. Sure. Sure.
Thank you.
So, thank you, sir. Thank you very much.
Okay. Thank you.
Participant, today assignment question I will host on the WhatsApp group now, right? If any other doubt, Sarma sir, once again.
Yeah, sure.
Okay, Renuka.
Thank
Hello, sir.
you.
Uh,
Yes,
Hello, sir.
ask to him.
Yeah.
Yes.
Sir, I have a question, sir.
Yeah.
If we want to use autoencoders for classification, is it possible, sir, for that
No,
application?
no, no. Autoencoder is not meant for classification. So if you want to have use classification, you want to design a classification, you have to either use learned file if it is an image, or uh, other stuff like RNN, LSTM, and Inception V3. So that kind of algorithms work for you if you are intended to use a classification. But if it is uh, just these things just for compressions and all.
Okay, so we can go for enhancement also can be done, no, sir, with this autoencoders?
Yeah, enhancement you can do it. Yeah, feature enhancement you can do it. Let's say if you have image stuff, and if you want to have a just to remove few things or highlight few things, you can do it.
Okay. Okay, thank you so much, sir.
Okay.
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 Any other doubt? Okay, sir. I think there is a no doubt.
Okay, fine.
Okay,
Thank
thank you,
you.
sir. Thank
So
you.
I'll share the data or link for these two, so you can just share with them. Okay.
Okay, sure,
Um,
sure,
so all these details I'm sharing with you.
sure. Okay,
Thank you so much. Have a nice day. Uh, All the best.
Okay, dear participant, thank you for cooperate with me. So assignment will post on the your WhatsApp group. Kindly you check it, right? Thank you to all.